tasks monitoring, analysis tools, and common optimization solutions. The products and services of our team will be delivered to all Android application development teams in ByteDance, and these will help them improve the application's user experiences. Today, my topic is about task scheduling optimizations in mobile applications. As multi-core CPU is widely used in Android mobile phone, multi-thread frameworks are seen everywhere to make better use of CPU resources. But in real scenarios, the utilization is not always as expected. It could be affected by different scheduling behaviors. In today's sharing, I'll introduce task scheduling customizations in Linux kernel carried out by community, Google, and chipset smartphone vendors. Then share our observation, analysis, and optimization methods for inefficient scheduling issues we've seen in Android applications. First, let's take a look at current status of Linux kernel schedule of Android. At the early stage of Android phone industry, there were dual-core or quad-core ARM architecture-based CPUs, as known as symmetric multiprocessors, and then octa or even more cores were packed into ARM CPU with big little architecture, and these were heterogeneous multiprocessors. Little processors are designed for maximum power efficiency, while big processors are designed to provide maximum computing performance. For the Linux scheduling in Android, we just use the mainstream version directly at the period of symmetric multiprocessor. But after heterogeneous multiprocessor coming into Android phone, scheduler needs to place the task to CPU core more properly. For example, background tasks like downloading, syncing should be put on little core to save power, and user experience sensitive tasks should be put on performance core for low latency. Then the scheduler is customized through AOSP, chip vendors like ARM, Qualcomm, and MediaTek, and smartphone vendors. So if we compare how tasks of the same application are scheduled on two smartphones, we may find obvious differences because of these customizations. Like I said, task placement is attached the greatest attention. For symmetric multiprocessor, we just need to care about load balancing, but for heterogeneous multiprocessor, we have to identify character of the task in an accurate and timely manner and make a decision. Take energy-aware scheduler, for example, which is now widely used and also called EAS. It relies on energy model to select an energy-efficient CPU for each task. As demonstrated in the diagram, which CPU core should a task with an estimated node run on? There are two choices, CPU core 1 and 3. If core 1 is selected, frequency must be moved up for both CPU 0 and CPU 1 as the current capacity can meet the demand and the CPU frequency is changed by cluster. If core 3 is selected, there is no need for frequency change, but the power may be higher because according to the energy model, power performance efficiency of big cluster at this point is higher. We can see that EAS has more bias on energy efficiency or more power conservation. Well, there are also some other customizations with different biases, like QHMP developed by Qualcomm. Tasks are scheduled according to their demands and marked as big or small tasks, which are calculated over several sliding windows and may have better performance and burst load. These simplified modelings may not work well at every scenario, like temporary thread or work thread in thread pool. Different kinds of work are put on it. It's hard to estimate or predict the load accurately. So some schedule policy based on control group is also introduced into Android to improve the scheduling. Basically, these control group policies help favor the foreground tasks and restrict the background tasks. Like one example of CPU set policy shown here in the left picture. Top application, which refers to the application that the user is currently interacting with, can run on any CPU cores. And background tasks are restricted to run on little cores, which means scheduler will mask big cores out and only place these tasks on little cores. Another example of policy is based on schedule. Schedule is a tunable parameter to balance task placement, trade-off energy efficiency for performance boosting. The value will be used as a weight when calculating the energy efficiency. We can set higher value for performance sensitive tasks while lower value for the others. In this way, the high schedule value tasks will be scheduled to because easier. Scheduling is even customized according to scenarios. Some heuristics and hints are designed and can be called in code path. For example, in scenarios like application launching or feed scrolling, the CPU frequency goes up step by step as the load increases. It may take hundreds of milliseconds to climb up to the highest frequency. If a perfect call is invoked at the beginning of these scenarios, then the frequency will be set to requested level immediately, which could help speed up task executing and reduce the latency of user interaction. Some specialized strategy is even designed for UI thread, heavy game thread, and critical service. Boost the priority of a related thread is a straightforward way. Let's look at a more complex problem. Imagine a log contention case. Task A is holding a log while some tasks are waiting to get the log. They are inserted into a FIFO queue as the log has no priority inheritance by default. If a UI thread is in the queue, it has to wait until all tasks before they are completed. Now, some optimization would mark the UI thread and insert it to the head of the waiters queue when a log contention happens. Then UI thread will get the log earlier. These customizations are only used in limited scenarios as they improve performance at the cost of more power consumption. Now let's look at multi-threading from Android applications perspective. Lots of framework libraries are adopted in Android application, and lots of threads could be created. As shown in the diagram here, during application launch, threads are created for initialization, data querying, library loading, networking, data deserialization, pixel decoding, and rendering. These tasks are being executed concurrently to speed up the application launch. At first, we could always make some improvements through multi-threading. As the application is becoming more complex and more threads are created, we may not go any further. Sometimes we may want to ask a question. Is multi-threading in Android application fully utilizing the multi-core CPU resource? From the scheduling data shown here, we can see that in a period of 1.4 seconds, the UI thread runs on CPU for 700 milliseconds, which is about half of the total duration, and spend other part of the time in sleeping state, uninterruptible sleeping state, and runnable state. Sleeping state means tasks is polling message waiting for a user space lock being blocked in IPC core or even actively calls the API. Uninterruptible sleeping state means task is waiting for a kernel space lock or IO driver walk to complete. And a runnable state means task is preempted or waked up from blocking state and not scheduled yet. And for the whole application process, the total runtime is less than 5 seconds. On the octa-core CPU, we think this is not good enough for a duration of 1.4 seconds. One typical issue we've observed is that sometimes too many tasks are packed on big cores, while leaving the little cores empty. This is because of aggressive scheduling strategy. Once triggered, the load estimating and power consumption are ignored. Tasks are placed on big cores as many as possible if the big cores are not masked out by CPU set. But the throughput may not be the best if there are lots of threads. Preempting, lock contention, and priority inversion would become more severe. Throughput would be higher if some async tasks are placed on little cores properly because of more context information in application. Identifying the importance of thread is possible, and the CPU topology class load are also available. Then we can reassign the threads to CPU cores based on this information. On some specific CPU, even L2 cache size is taken into account. As some octa-core CPU looks like symmetric multiprocessor, two clusters have the same architecture and the same frequencies, but the two clusters have different L2 cache size. So the performance would be much better on big cache size cluster if the memory access is the bottleneck. Then let's take a look at priority inversion in complex situations. UI thread is waiting for some async task to complete, and the async task is waiting for a lock when executing. Well, there are lots of waiters at the front of async task. The lock owner has been preempted for a long time because of low priority. We can see that priority inversion happens. In Java SDKs of Android, there is no priority inheritance for synchronizations or locks by default. And in C level, there is also no support in pthread mutex, although there is a priority inheritance protocol in futex, but it is not so convenient to use. And priority inheritance is supported for pthread mutex in Bionic C library recently, but not widely used yet. We can add priority inheritance for Java synchronizations by wrapping futex, and sometimes even simple priority guard is good enough. That means adding priority floor or roof for critical section. We have also seen some bugs that set threads to unexpected priority, which leads to background tasks preempting foreground tasks. Priority guard will also help for these issues. Another issue we observed is about short lifetime tasks or threads. As statistics of an application launch shows here, many threads only survive for about 30 milliseconds within 2 seconds, and less than 20% of the short period is in running state. We can find from trace that threads are preempted or blocked at most of the time. And because many of these tasks are offloaded from UI thread, if the task is delayed, UI thread may have to wait for the completion and then go on executing. For this issue, we've tried an optimization method called thread quota. As we observed, many threads only live for a short period, so we can just set high priority to a thread just after birth. Then a timer is set up. After time cycle, a sigprof signal is triggered and the priority is re-evaluated based on multiple factors, including the scheduling statistics, current priority, and total workload. With thread quota, short lifetime threads could run more efficiently and whole throughput of the process is improved. One more issue I want to talk is about page fault. As we tested, thousands of page faults happen concurrently in a second during an application launch. Lots of memory or pages are accessed for the first time during launch. For example, an object is allocated on Java heap and the area is never touched. Or the Java application code is mapped into address space and then loaded into memory along with the execution path. For these cases, page faults happen because virtual memory is allocated while no physical page is mapped with the virtual page. When we break down the time cost of page fault, we found that most of the time is spent on uninterruptible sleep, waiting for a global read-write semaphore, which is designed for protecting the change of memory maps across the process. But since it's a read-write semaphore, and suppose most of the accesses are read, holding a read semaphore will not block another one. Why does it still cost so long? We collect more detailed traces and find that there are also lots of write actions and these will block all read actions, as shown here. System calls like memory map, memory unmap, memory protect, memory advise need hold write semaphore and all the tasks need a read semaphore have to wait and the waiting queue will be very long. And if the task is preempted when holding a write semaphore, the situation would be even worse. To optimize the memory address space global lock of a process, the Linux kernel community has been trying for years. For example, there is an effort called speculative page fault. As described in the commit, the idea is to handle user space page faults without holding the memory map semaphore. This should allow better concurrency for a massive threaded process, since the page fault handler will not wait for other threads' memory layout changes to be done. And it is also adopted in ARM architecture for Android, and we found that it is applied on a few devices. Since its stability is still under verification and not maintained yet, it's not implemented in most of the devices. So could we also do something to improve this issue at applications side in user space? First, let's look deeper into the details behind general page fault and see where the page faults come from. We instrumented more traces and got data for an application launch. More than 1,000 page faults with log contention on UI thread and cost about 300 milliseconds in about 1 second, and more than 10,000 page faults with no contention for the whole process. Among page faults on UI thread, about 30% are caused by code file accessing, including application bytecode file, AOT compiled file, native libraries, and about 30% are caused by heap accessing, including Java and native malloc heap space, and about 6% are from other memory areas such as picture resources, font files, and private areas. For file maps and heap space, most of the operations are read or update the content, while no change of memory areas is needed after application. Well, when a file is mapped into address space, the area is almost fixed unless it needs to expand or remap. And Java heap space is also fixed after application process is created. There should be no write log contention, and all read log could be held concurrently without blocking. So what happens here? Take Java heap for example. 4 threads allocate objects at the same time. Each of them can allocate memory through a local allocation buffer, which could help allocate memory without locking a global area. After allocation, if the address is accessed for the first time, then a page fault will be triggered. Although it's concurrent in user space, it could be all blocked in kernel space waiting for the memory map read semaphore, because write semaphore is held as the code path of memory map or memory protect. This can also explain what happens to code files and other page faults. After better understanding this issue, we can optimize it accordingly. For code file, a straightforward idea is doing some preload. But if we review this idea again, we can find that I/O preload reduces the time from disk to memory, but the file is loaded into page cache. The map between virtual page and the physical page is not set up. However, we can just get the map address of a file, identify the hot accessing range, and do something that will lead to page fault. Memory advice may be an option and which is also introduced in latest Android version by Google, but test results are not always in line with expectations. An easier way is just reading once for each page, and it could be more efficient if combined with some binary layout optimizations. For Java heap, it's more complex because first, the heap space is inherited from its parent process, and reading the area will not come with a physical page allocated from a page fault. It just reads from the parent page if it exists, and writing to this area can work, but could erase the original content. And another complex thing is identifying the hot range. This can be solved by investigating the allocation algorithm. At last, we choose memory lock system call to pre-page for some areas of the Java heap. Then we call memory unlock to cancel the side effect of memory lock. After the optimizations, much less page faults lock contentions are left, and the overall throughput is also improved. From the issues and optimizations I just introduced, we can realize that for scheduling problems, kernel scheduler could be enhanced in a more general way based on a broader view of the system's current load. From applications perspective, more specialized optimizations could be done based on more specific context information to handle the problems like burst load, extreme concurrency, and complex priority inversion. And another thing is about tools. Tools are very important in debugging and analyzing these kind of issues as the information cannot be observed directly. We need to improve trace tools to visualize information across the software stack clearly and aggregate data conveniently. This is all I'd like to share today. Hope this could help with some related problems. Thank you.
Thank you so much, Nian. That was a very, very deep dive into scheduling of work across Android. So I think we have a couple of questions. I would start with the first one about the Android fragmentation, right? So there's fragmentation on the software level, different versions of Android all over the place that your app has to run on top of, fragmentation in hardware. So when you're talking about the different scheduling options, are they available everywhere, or you kind of have to be mindful of where is your app running?
Yeah, for this question, my answer is no. It's not available everywhere because, as you mentioned, Android is very fragmented, and for the devices years ago, the schedule options is quite different with EAS. Google and ARM have put big efforts developing the EAS scheduling to the new Android version, right? So we need to mind the differences of the scheduling options.
Okay. And that means you have to go into an ugly if this version of chipset and this version of Android, then turn on this option. Is that kind of how you run? How did you?
No, we are not doing in this way because the schedule options are not available to application side, right? We can modify the application the scheduling options. So we are doing through system calls to modify the scheduling behavior in application side.
Got it. All right. Let's see. Second question we had, I think, was around the trade-off, energy versus performance. So I think that's a trade-off that actually might change in the life of a user, right? In the morning, when I just wake up, my phone is fully charged up. I just want to get up to speed very quickly on what's new. Towards the end of the day, I'm out of battery. I just want to make sure it can keep running until I get home to charge it again. So are you able to change the trade-offs a bit on the fly, or the trade-off is baked into the app when you build it?
I think this question should be answered in two sides. One side is the system side, right? I think that the big impact is come of the the energy performance trade-off is come from the system design. I think the system has many options to balancing the power consumption and the performance, and boost the performance for some critical scenarios. And but for the application side, we can't modify the trade-off. We just be care of the power consumption while we are trying to optimize some scenarios. And it's our work is doing the runtime, not the build time. Yeah, we are
Okay.
doing that dynamically. Yeah.
That is really cool. And last question I saw in the Q&A group is around short life tasks. So I'm wondering, you're saying we spin off lots of small threads that are very short-lived. The system kind of deprioritize them. So you're saying, okay, let's change the way the schedule kind of looks at those tasks. But is there maybe another hack, which would be, as we kind of spin off the work to different threads, we can aggregate several workloads so the threads are not short-lived? Would that be a more efficient hack?
Yeah, I agree that we should do we should design better framework to pack more works together and to improve the efficiency from the application implementation. Right, I agree. And actually, there's also some engineers is working on this in balance. And but the truth is, there is also some thing is done by some third-party libraries works. We can't modify their behaviors, or it's hard to modify their behaviors. So we can cover these kind of behaviors through our scheduling optimizations.
Okay, so it's better to try to fix it at the source. I know, for instance, startup is where, in our side, we spend a lot of time trying to make it faster. So that's why I guess there we try every hack possible just to squeeze a few more milliseconds. All right. Listen, thank you very much. Thank you very much for your time this morning. Hang around for the panel talk.
Thank you for listening.
And now let's